Once this particular equation is solved, one gets the value of energy E and the wave function psi. The solutions, the wave functions, psi's, essentially represent the atomic orbital in an atom, and these atomic orbitals in an atom which come out of as a consequence of the solution of this particular equation also carry three quantum numbers: n, the principal quantum number; L, the azimuthal quantum number; and M, the magnetic quantum number associated with the system. So what are these quantum numbers? So as I've just said, n is the principal quantum number which actually designates the size of the orbital and its energy. It has integer values, just integer values like 1, 2, 3 and so on, goes up to infinity. So if the value of the n is large, it is more distant from the nucleus and it corresponds to the quantum numbers associated with the Bohr's model. The second quantum number is the orbital angular momentum quantum number L, which describes the shape of the atomic orbital. It can have integer values starting from 0 and going up to n minus 1. So if n is 3, then it can have values like 0, 1 and 2. So associated with every such value of L, we associate a definite shape, we associate a definite letter mark. Say for example, if L is 0, we call this as the S sublevel or an S orbital. If L is 1, we call it a p orbital. If L is 2, we call it a d orbital. And if L is 3, we call it an f orbital. The third quantum number that comes into picture is the magnetic quantum number ML, and this ML describes the orientation of this orbital in three-dimensional space. So ML can have values going from minus L to plus L, including the 0. Okay, so this is a table which gives you an idea, which gives you a representation of the possible values of L and ML depending on the value of n over here on the leftmost column. So with these quantum numbers in force, we observe that for n equal to 1, we can have only one subshell, we can have only one orbital, s orbital. For n equal to 2, we can have distinctly two different kinds of orbitals, s and p. If you go over to n equal to 3, you can have three different sorts of orbitals, s, p and d, and going over to n equal to 4 leads to four different classes of orbitals having four different shapes, and the f orbitals comes into picture. So there is yet another quantum number which was not a consequence of the solution of the Schrödinger equation directly, but it was a consequence of some sort of an experiment called the Stern-Gerlach experiment, which showed that electron has got some sort of an intrinsic angular momentum of its. So this intrinsic angular momentum of the electron is called its spin. So it was observed that there is yet another quantum number which we call as the ms, and this ms represents the electron spin. Ms can enjoy only two distinct values, plus half and minus half. So this is a strikingly different quantum number where the quantum number is not an integer, rather it's a fraction, and it's a constant fraction of half or minus half. So electrons will spin opposite to each other in the same orbital. So let us take up a question. So which of the following are the possible sets of quantum numbers that are allowed? So I have given you three options, and this is one of the options, this is another, and this is the third one. So if you just study this, you see this is the value of n, l, ml and ms. So likewise here are the same thing. So if you see n is 1, then l cannot be 1. So this particular option A is an incorrect option, since n1 is always associated with only 1 and a specific value of L, that is L is 0. But all these other two possibilities can be there. So now let us come to the shape of these atomic orbitals. Atomic orbitals, depending on what value of L they enjoy, have definite shapes. Firstly, the s orbital is spherically symmetric in shape. The p orbital has got two lobes of opposite sides, of opposite phases around the nucleus. D orbitals have more variations of lobes depending on what kind of d orbitals you are looking at. You can be having actually 4 such lobes, and there is one d orbital which we know as the dz square orbital. This has got 2 lobes and a Saturn ring kind of structure in it, and f orbitals are genuinely complex in structure. So let us see what these orbitals look like. So these are essentially representations of some s orbitals, say for example cut into pieces. So if you look at the inside, this core, say start with this is essentially the 1s orbital. So this dark portion is the nucleus. It has been cut, it used to be a sphere, it has been cut. So this dark portion is the nucleus, and this region is the region where the electron can reside. If you go over to this structure, there is a dark core inside over here where the pointer lies. This is the nucleus, and you can see that there are zones like this, whitish zones. These are the zones where there are nodes. I'll talk about the nodes. And similarly, if you go over to the 3s orbitals and so on. So these are the shapes of the p orbitals. These are the 2 lobes. Here lies the nucleus. One of these lobes, say this one, if this represents the positive phase of the wave, then the other lobe must represent the negative phase of the wave, and this is true for the other 2 as well. These are the shapes of the d orbitals. This is the dxy orbital lying on the xy plane. This is the xz orbital aligned along the xz plane. This is the yz orbital along the yz plane, and so on. And this is the dx square minus y square which lie along the xy axis, and this is a specifically different kind of a d orbital. I mean, its structure is different. This is a dz square orbital which has got 2 lobes, and it has got a Saturn ring kind of structure over here. So let us start with the electronic configuration. So what is an electronic configuration? Every atom in its ground state, the electrons enjoy the lowest energy state. In the excited states, the electrons are promoted to the higher energy orbitals. So electronic configuration essentially means how these electrons are distributed in the various atomic orbitals. Fine. So let us compare this description with the line spectrum. So that was experimentally observed. So let us take up the electronic configuration over here. So for the minimum value of energy, n is 1, and there can be one possibility of orbital coming up, and that was the s orbital. If you go over to n is equal to 2, and there can be 2 possibilities, s orbitals and the p orbitals. The 2s and 2p orbitals are slightly different in energy. If you go over to n is equal to 3, there can be 3 orbitals, s, p and d, while the energy difference in between 3s and 3p is very little. The difference between 3p and 3d is appreciably higher. In between, see, the structure of the orbitals are such, their three-dimensional disposition in the three-dimensional space is such that in between the 4s orbitals comes into picture. So it is some sort of an arrangement where it is not just the principal quantum number that determines the relative energies of these orbitals. There is something else to it. So in an attempt to simplify matters, we have actually arranged this in what we today know as the Aufbau principle, where we have a definite pattern to fill up these electrons in these orbitals. And while filling up these electrons in these orbitals, we take into account a very important principle which is known as the Pauli exclusion principle. Pauli exclusion principle says that no 2 electrons in a particular atom can have all the 4 quantum numbers n, l, ml and ms to be equal, and there can be no more than 2 electrons in an orbital. Fine. So with this in force, and in addition, there is the Hund's rule of maximum multiplicity, that is the most stable arrangement for the electrons in orbitals of equal energy or in degenerate orbitals is where the electrons enjoy the maximum spin. So with this idea in force, if we go and fill up these electrons, say for example, carbon, it has got 6 electrons. So 1s, 2s and 2p are the orbitals. So firstly, if you take into account the Pauli exclusion principle, this particular electron on the left has an n value of 1, L value of 0, that means s orbital, ml value of 0 and ms value of plus half. So in an attempt to take into account the Pauli exclusion principle, the first 3 quantum numbers remaining the same, the fourth quantum number, that means ms, should be minus half, hence its downspin. So a value of plus half of ms will be represented by an upspin or an upside arrow, and a downside arrow will represent an ms value of minus half. And likewise, we do the same. See, while filling up, one could have really paired these 2 electrons in these orbitals, but that cannot be done by virtue of the Hund's rule, which says that the most stable configuration is the one which actually allows the maximum spin. Because if you try to pair it up over here, it will enhance the interelectronic repulsion and will energize the atom, and it won't be the lowest energy state anymore. So what are the rules for writing the electronic configurations? So the electrons will be residing, they will be staying in the orbitals of lowest possible energy. Maximum 2 electrons per orbitals are allowed, and electrons do not pair in degenerate orbitals like this. They are not allowed to pair in the degenerate or same energy orbitals, and orbitals fill in a definite pattern. So this is the pattern over here. So you start filling from here. This is a 1s. You put 2 electrons here. You go over to 2s. So this arrow will turn to this end like this. Then once you have filled 2s, fill 2p. So these are in the same energy state. Once 2p is over, go over to 3s. Once 3s is done, do it for 3p and then go over to 3 and 4s. So if you just take up certain examples of filling up process. So let us write down the electronic configuration associated with 3 distinct cases where the first atom has got an electron number of 20, the next one 35 and the third one 26. Firstly, see for z equal to 20. So it's a simple case, a very simple case in fact. So you have 1s, 2s, 2p, 3s, 3p and 4s. Keep in mind that you have to proceed along these lines. So once 3s is done, you go over to 4s, 3p, 3d and so on. So you keep on filling them. So this is a simple case. If you go over to 35, then up to this is simple. Fill 4s ahead of 3d, then fill 3d and then go to 4p. The case of atomic number 26 is a bit different. Now see, in case of this, you fill up all these 4s and 3d. Fine. Now, these electronic configurations that we perform, we actually fill up in this manner is a basis of the modern form of periodic classification. This periodic classification of elements is dependent entirely, the modern form I mean, is dependent entirely on the kind of way we have filled up these electrons. So position on the periodic table is always a good indicator, is always a very good indicator of the electronic configuration. And these electronic configurations dictate or they determine the actual properties associated with these elements. So if you look at the periodic table, this group of these alkali metals followed by the alkaline earth metals and this chunk starting from scandium going over to zinc and going down like this chunk is a representation of the corresponding transition metals. If you go over to this side, this blue one and this a little bit orange ones, you get a particular case where you have mostly the gases, and if you go down, they become solid and they become more metallic. And coming over from here, from lanthanum onwards, this represent the F block elements. So these are the locations where the F block elements come into picture. Okay. So electronic configurations and these noble gas configurations, they can be done in a way that we have said. So for example, if you write Z is equal to 15, you can see that this portion is neon and the rest is like this. So in accordance with the periodic table, this part, the alkali and the alkaline earth metals, these have these s orbitals only. They have incompletely filled d orbitals over here, the transition metals. They have the p orbitals coming into force, and these have the f orbitals. So in accordance with the filling up process, you can classify the entire periodic table by means of this. Well, there are certain exceptions. Certain exceptions like copper. Copper has an atomic number of 29. So you can have argon and then you start filling up. So if you go by the rule, then you should be having 4s2 and 3d9. So that's the case. But copper exists as 4s1 3d10 because there is a reason behind it. This d10 configuration gives copper an additional stability. So if you have an option of stabilizing this d orbital to some additional extent, take up that option. The same is the case with chromium, which is an atomic number of 24. The same again argon over here. So you would have actually done 4s2 3d4. But see, if d10 is stable, d5 assumes half the stability. So allow it to go for half the stability and make it 4s1 and 3d5. So there are certain key points that one has to note. The electromagnetic spectrum, the wavelength, frequency, energy distribution, light is a quantum, the photoelectric effect, the emission spectrum, ground versus excited state, the Heisenberg's principle. And very importantly for atomic structure, the disposition of these quantum numbers n, l, ml and ms. And while filling up, while writing the electronic configuration, take into account three principles: the Pauli exclusion principle, the Hund's rule and the Aufbau principle. And these are the shapes of p orbitals as I have just said. So these are the d orbitals. And here is a table which will be actually a shorthand for you to understand the nature of these orbitals. So there are certain problems also in quantum mechanics, the interelectronic interaction problems. It's very hard to determine the exact value of the interaction. So there cannot be exact solutions. And one last important thing that I would like to mention is these are certain books which I will recommend you for further study. In addition, if you just study the entire thing of electronic structure, you will observe one thing, that entire chemistry depends on a very important assumption, that all elements in the periodic table are having orbitals which are hydrogen-like, because hydrogen atom is the only atomic problem in quantum mechanics that can be solved exactly. Thank you.